Welcome! In this session, we'll explore a fascinating problem, problem number 1855, maximum distance between a pair of values. We'll dive into the intuition behind the solution, analyze various approaches, and understand their complexities. Let's get started. The problem asks us to find the maximum distance between a pair of indices, I, j, from two given arrays nums1 and nums2. These arrays are sorted in non-increasing order, meaning the values decrease as the indices increase. The key condition is that for any valid pair, I, j, not only must I be less than or equal to j, but also the value at nums1, I, must be less than or equal to the value at nums2, j. If these conditions are satisfied, the distance is calculated as ji. Our task is to find the largest possible distance across all such valid pairs, or return 0 if no such pair exists. The input consists of two arrays, nums1 and nums2, and the output is a single integer, the maximum distance. Let's look at some examples to better understand this problem. In the first example, nums1 is 55, 30, 5, 4, 2, and nums2 is 100, 20, 10, 10, 5. To compute the maximum distance, we iterate over each index I in nums1 and find the largest index j in nums2 such that the value at nums1, I, is less than or equal to the value at nums2, j. For instance, when I equals 0, the largest j satisfying the condition is j equals 2, giving a distance of 2. Similarly, for I equals 1, the largest valid j is 1, resulting in a distance of 0. For I equals 2, the largest j is 4, giving another distance of 2. Among all these distances, the maximum is 2, which is our output for this example. Next, we'll explore another example to deepen our understanding. In the second example, nums1 is 2, 2, 2, and nums2 is 10, 10, 1. Again, we compute the maximum distance by checking each I in nums1 and finding the largest valid j in nums2. For I equals 0, the largest j is 1, resulting in a distance of 1. For I equals 1, the largest j is again 1, giving a distance of 0. Similarly, for I equals 2, the largest j is 2, which also results in a distance of 0. The maximum distance in this case is 1. Let's now examine a third example to see how the logic applies to different inputs. In the third example, nums1 is 30, 29, 19, 5, and nums2 is 25, 25, 25, 25, 25. For I equals 0, we find that the largest j satisfying the condition is j equals 2, resulting in a distance of 2. For I equals 1, the largest j is 3, which also gives a distance of 2. Similarly, for I equals 2, the largest j is 4, resulting in another distance of 2. The maximum distance is therefore 2. To summarize, the problem involves iterating through potential pairs, I, j, while respecting the constraints, and the goal is to maximize the distance ji. Constraints such as array length and edge cases, like arrays of length 1 or arrays with identical elements, must be handled efficiently to ensure correctness and performance. To begin solving the problem, one of the most intuitive approaches we can consider is the brute force method. The idea here is simple: we check all possible pairs of indices, I, j, such that I equals j. For each pair, we verify if the condition nums1, I, equals nums2, j, holds true. If it does, we calculate the distance ji and keep track of the maximum distance encountered so far. The process involves iterating over every index I in nums1 and, for each I, iterating over all valid indices j in nums2. While this approach is straightforward to implement, its main drawback lies in its inefficiency. Since it involves a nested loop structure, the time complexity is n squared, where n is the length of the larger array. This quadratic complexity makes the approach impractical for large inputs. On the bright side, it uses no additional space, so the space complexity is 1. Ultimately, while this method is useful for understanding the problem, its inefficiency means it's not the best choice for real-world scenarios with large datasets. Now, we consider a more efficient solution, the two-pointer approach. This method takes advantage of the fact that both nums1 and nums2 are sorted in non-increasing order. By leveraging this property, we can eliminate redundant comparisons and systematically find valid pairs. The key insight here is that if nums1, I, equals nums2, j, for some pair, I, j, then this condition will also hold true for all indices k equals j and nums2 because the array is sorted. On the other hand, if nums1 I, nums2 j, it means that the value at nums1 I is too large to satisfy the condition, so we increment I to explore a smaller value. Using this strategy, we initialize 2 pointers, I for nums1 and j for nums2, both starting at 0. As we iterate, if the condition nums1 I equals nums2 j holds, we calculate the distance j I and update the maximum distance. Then, we increment j to explore larger indices in nums2. If the condition doesn't hold, we increment I to try a smaller value in nums1. This systematic approach ensures that we explore valid pairs efficiently. Analyzing the performance of the two-pointer approach, we find that it is extremely efficient. The time complexity is O(n), where n is the length of the larger array. This is because each pointer moves through its respective array at most once, making the traversal linear in time. Additionally, the space complexity remains O(1), since we don't use any extra data structures or allocate additional space. The two-pointer method is optimal for this problem because it leverages the sorted property of the arrays to minimize unnecessary computations. By avoiding redundant checks, it ensures that we achieve the best possible efficiency while maintaining clarity in implementation. This makes it well suited for handling large arrays, even with lengths up to 10 to the power of 5. Overall, the two-pointer approach strikes an excellent balance between simplicity and performance. In conclusion, the chosen strategy for solving this problem is the two-pointer approach. This method stands out as the optimal solution due to its linear time complexity and minimal space usage. The key advantage lies in its ability to exploit the non-increasing order of the arrays, allowing us to efficiently explore valid index pairs without redundant checks. While the brute force approach provides an intuitive starting point, its O(n)² time complexity renders it impractical for large inputs. By contrast, the two-pointer technique ensures we adhere to the problem's constraints, making it highly scalable for arrays of significant length. In summary, the two-pointer approach is both time-efficient and straightforward to implement, making it the ideal choice for this problem. In this problem, we are given two non-decreasing arrays, nums1 and nums2. Our task is to find the maximum index difference, defined as ji, where I is less than or equal to j, and the value at nums1 I is less than or equal to the value at nums2 j. The challenge is to solve this efficiently, leveraging the sorted nature of the arrays. A straightforward approach is the brute force method, where we check every possible pair of indices, I, j, to find the maximum distance. For each pair, we verify if the condition nums1 I equals nums2 j is satisfied. If it is, we calculate the distance j I and track the maximum distance encountered. While simple, this approach has limitations in terms of efficiency, as it involves iterating through all possible pairs, making it computationally expensive for large arrays. To implement the brute force solution, we start by initializing a variable, max_distance, to 0. This will store the largest valid distance we encounter. Then, we use two nested loops. The outer loop iterates through each index I in nums1, and the inner loop iterates through all indices j such that j is greater than or equal to I. For every pair, I, j, we check if the condition nums1 I equals nums2 j holds. If it does, we calculate the distance j I and update max_distance if the new distance is larger. Once both loops complete, we return the value of max_distance. However, this approach has a time complexity of O(n)² due to the nested loops, which makes it impractical for larger inputs. On the other hand, the space complexity is O(1), as we do not use additional data structures. A more efficient solution is to use the two-pointer technique, which optimizes the process by eliminating redundant comparisons. Here, we take advantage of the fact that both arrays are sorted in non-decreasing order. We use two pointers, I and j, which start at the beginning of nums1 and nums2 respectively. The idea is to increment j to find the farthest valid index for each I while ensuring the condition nums1 I equals nums2 j is satisfied. This avoids the need to restart the comparison for each I, significantly reducing the number of checks. During this traversal, we calculate the distance j I whenever the condition is met and update max_distance if the new distance is greater. If the condition fails, we increment I to find a smaller value in nums1 that might satisfy the condition with the current or subsequent values in nums2. At the end of the traversal, we return the maximum distance found. The two-pointer approach provides significant improvements in efficiency. With this method, the time complexity is reduced to O(n), as each pointer traverses the arrays only once. The space complexity remains O(1), as the algorithm uses a constant amount of memory. Several key insights make this approach effective. First, it leverages the sorted nature of the arrays, allowing us to skip redundant checks by moving the j pointer forward instead of restarting for each I. Second, it handles edge cases gracefully. For instance, if either array is empty or if no valid pair, I, j, exists, the algorithm returns 0. Additionally, it accounts for scenarios where all values in nums1 are greater than those in nums2. Lastly, the monotonic property of the arrays ensures that once the condition nums1, I, nums2, j, fails, no subsequent values of j will satisfy the condition for that I, justifying the need to increment I. This algorithm relies on simple data structures to achieve efficiency. The two integer pointers, I and j, allow us to traverse the array systematically while minimizing space usage. Additionally, a single variable, max_distance, is used to track the largest valid distance encountered during the traversal. To illustrate how this works, consider an example with the input arrays nums1 equals 2, 2, 3, 5, and nums2 equals 3, 5, 6, 6. Using this input, we will walk through the algorithm step by step to observe how the two-pointer technique efficiently identifies the maximum index difference. In this example, we initialize I and j to 0 and set max_distance to 0. First, we compare nums1, 0, which is 2, with nums2, 0, which is 3. Since the condition 2 equals 3 is satisfied, we calculate the distance ji, which is 0. The max_distance remains 0. Next, we increment j to explore further. Now, we compare nums1, 0, with nums2, 1, 5. The condition is still satisfied, and the distance is 1 and 0 equals 1, so we update max_distance to 1. We continue this process, incrementing j and comparing values, until the end of the arrays. By the final step, the maximum distance is found to be 3. This example demonstrates how the two-pointer technique efficiently handles the problem, leveraging the sorted properties of the arrays to reduce complexity from O(n)² to O(n), making it well-suited for large inputs. This solution uses the two-pointer technique to efficiently find the maximum distance between a pair of indices in the given non-decreasing arrays nums1 and nums2. Here, I and j start at the beginning of their respective arrays. The algorithm iterates through the arrays while maintaining the condition I equals j. If the condition nums1, I, equals nums2, j, is satisfied, the algorithm calculates the distance j, I and updates the max_dist variable if the current distance is larger. The pointer j is then moved forward to explore larger distances. If the condition is violated, the pointer I is incremented to try to restore the condition. This ensures that the pointers always move in a way that respects the sorted order of the arrays. The algorithm stops when either pointer reaches the end of its respective array. Since each pointer traverses its array at most once, the time complexity of this solution is O(n plus m), where n and m are the lengths of nums1 and nums2. This makes the solution efficient for large input sizes. The space complexity is O(1), because no additional data structures are used. This is the Java implementation of the LeetCode problem maximum distance between a pair of values. The logic mirrors the Python solution, using two pointers to efficiently iterate over the arrays. The main differences include explicit type declarations, usage of Java collections, and Java's built-in math library for computing the maximum distance. The implementation ensures optimal performance and conciseness. We start with the first example where nums1 is 10, 8, 6, 4, and nums2 is 12, 9, 8, 3. Both I and j are initialized to 0, and max_dist is set to 0. In the first iteration, we compare nums1, I, and nums2, j, which are 10 and 12, respectively. Since 10 is less than or equal to 12, the condition is true. We calculate max_dist as the maximum of the current max_dist, which is 0, and the difference ji, which is also 0. So, max_dist remains 0. Then, we increment j to 1. In the second iteration, with I still at 0 and j now at 1, we compare nums1, 0, and nums2, 1, which are 10 and 9. This time, the condition is false because 10 is greater than 9. As a result, we increment I to 1 without updating max_dist. In the third iteration, I is now 1 and j is still 1. We compare nums 1, 1, and nums 2, 1, which are 8 and 9. Since 8 is less than or equal to 9, the condition is true. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 0. So, max_dist stays the same. Then, we increment j to 2. In the fourth iteration, I remains at 1 and j is now 2. We compare nums 1, 1, and nums 2, 2, which are 8 and 8. The condition is true because 8 is equal to 8. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 1. This updates max_dist to 1. We then increment j to 3. In the fifth iteration, I is still 1 and j is now 3. We compare nums 1, 1, and nums 2, 3, which are 8 and 3. This time, the condition is false because 8 is greater than 3. So, we increment I to 2, leaving max_dist unchanged. In the sixth iteration, I is now 2 and j is still 3. We compare nums 1, 2, and nums 2, 3, which are 6 and 3. Since 6 is greater than 3, the condition is false. Therefore, we increment I to 3 without updating max_dist. At this point, both I and j are 3, and the loop terminates. The final value of max_dist for this example is 1. Now, moving to the second example, nums 1 is 5, 4, 3, and nums 2 is 9, 8, 7, 3. Again, we initialize I and j to 0, and max_dist to 0. In the first iteration, we compare nums 1, 0, and nums 2, 0, which are 5 and 9. The condition is true because 5 is less than or equal to 9. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 0. So, max_dist remains 0. We then increment j to 1. In the second iteration, I is still 0 and j is now 1. We compare nums 1, 0, and nums 2, 1, which are 5 and 8. The condition is true because 5 is less than or equal to 8. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 1. This updates max_dist to 1. We then increment j to 2. In the third iteration, I remains at 0 and j is now 2. We compare nums 1, 0, and nums 2, 2, which are 5 and 7. Again, the condition is true because 5 is less than or equal to 7. We calculate max_dist as the maximum of the current max_dist 1 and ji, which is 2. This updates max_dist to 2. We then increment j to 3. In the fourth iteration, I is still 0 and j is now 3. We compare nums 1, 0, and nums 2, 3, which are 5 and 3. This time, the condition is false because 5 is greater than 3. So, we increment I to 1 without updating max_dist. In the fifth iteration, I is now 1 and j remains 3. We compare nums 1, 1, and nums 2, 3, which are 4 and 3. Since 4 is greater than 3, the condition is false. As a result, we increment I to 2. In the sixth iteration, I is now 2 and j is still 3. We compare nums 1, 2, and nums 2, 3, which are 3 and 3. This time, the condition is true because 3 is equal to 3. We calculate max_dist as the maximum of the current max_dist 2 and ji, which is 1. Max_dist remains 2. We then increment j to 4. At this point, j is 4 and the loop terminates. The final value of max_dist for this example is 2. Now, let's look at the third example where nums 1 is 3, 2, 1, and nums 2 is 3, 2, 1. As before, we initialize I and j to 0, and max_dist to 0. In the first iteration, we compare nums 1, 0, and nums 2, 0, which are both 3. Since 3 is equal to 3, the condition is true. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 0. Max_dist stays 0. We then increment j to 1. In the second iteration, I is still 0 and j is now 1. We compare nums 1, 0, and nums 2, 1, which are 3 and 2. Since 3 is greater than 2, the condition is false. So, we increment I to 1 without updating max_dist. In the third iteration, I is now 1 and j is still 1. We compare nums 1, 1, and nums 2, 1, which are both 2. The condition is true because 2 is equal to 2. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 0. Max_dist remains 0. We then increment j to 2. In the fourth iteration, I remains at 1 and j is now 2. We compare nums 1, 1, and nums 2, 2, which are 2 and 1. Since 2 is greater than 1, the condition is false. So, we increment I to 2 without updating max_dist. In the fifth and final iteration, I is now 2 and j is still 2. We compare nums 1, 2, and nums 2, 2, which are both 1. Since 1 is equal to 1, the condition is true. We calculate max_dist as the maximum of the current max_dist 0 and ji, which is 0. Max_dist remains 0. We then increment j to 3. At this point, j is 3, and the loop terminates. The final value of max_dist for this example is 0. This concludes the step-by-step walkthrough of the solution approach for finding the maximum distance between a pair of values in these examples. The time complexity of the solution is derived from the two-pointer technique used to determine the maximum valid distance between indices in nums 1 and nums 2. Here's how it works. We have 2 pointers, I and j, starting at the beginning of their respective arrays. For each iteration of the while loop, one of these pointers moves forward. If the condition nums 1, I, equals nums 2, j, is true, the pointer j increments, otherwise, the pointer I increments. Importantly, both pointers only move forward, and each can increment at most once per iteration. The loop itself terminates when either I reaches the end of nums 1 or j reaches the end of nums 2. This means the total number of iterations is at most the sum of the lengths of the two arrays, n plus m, giving the algorithm a time complexity of O, n plus m. In terms of space complexity, the algorithm is highly efficient. It uses only a constant amount of extra space throughout its execution. Specifically, we maintain 3 variables, max_dist to track the maximum distance, and I and j as the 2 pointers. Since no additional data structures or recursive calls are utilized, the space required does not grow with the input size. As a result, the space complexity is O1. This makes the solution not only time efficient but also memory efficient. To better understand the algorithm's performance, let's analyze the best and worst case scenarios. In the best case, all elements of nums 1 are less than or equal to their corresponding elements in nums 2. Under these conditions, the pointer I doesn't need to move forward, and the loop runs in O, m, time, where m is the length of nums 2. While the time complexity remains O, n plus m, the actual runtime is minimized. On the other hand, the worst case scenario happens when the condition nums 1, I, equals nums 2, j, fails frequently. This causes both I and j to move forward multiple times, but even in this case, the pointers still traverse the arrays linearly. Thus, the time complexity remains O, n plus m, ensuring the algorithm's efficiency across all cases. When comparing this approach to a brute force method, the efficiency of the two-pointer technique becomes even more evident. A brute force solution would involve iterating through all possible pairs of indices, I, j, such that I equals j and checking the condition nums 1, I, equals nums 2, j, for each pair. This requires a nested loop. The outer loop iterates over all indices of nums 1, O, n, and for each index, the inner loop iterates over all indices of nums 2, O, m. Consequently, the brute force approach has a time complexity of O, n asterisk m, which becomes computationally expensive for larger inputs. In contrast, the two-pointer method leverages the sorted nature of the arrays to avoid redundant comparisons, reducing the time complexity to O, n plus m. This is a significant improvement and highlights the power of optimizing with data structure properties in mind. Finally, let's solidify our understanding of the time and space complexity with a mathematical proof. First, consider the movement of the pointers. Each pointer, I and j, moves forward exactly once per iteration of the loop. The total number of movements for I is bounded by the length of nums1, which is n, and similarly, the total movements for j are bounded by the length of nums2, which is m. Therefore, the total number of pointer movements is at most n plus m. Next, the operations performed within each loop iteration, such as comparisons and pointer updates, take constant time, or O1. Multiplying the number of iterations by the cost per iteration gives us an overall time complexity of O, n plus m. Regarding space, the algorithm doesn't allocate or use additional memory beyond a few variables, so the space complexity remains O1. This proves that the two-pointer approach achieves optimal efficiency both in terms of time and space, making it far superior to the brute force alternative. When solving this problem, there are several common mistakes to watch out for. First, relying on a brute force approach to check all possible index pairs, I, j, is often where beginners start. While it might work for small inputs, the O, n squared, time complexity makes it impractical for larger datasets. Instead, look for ways to optimize, such as using binary search or prefix sums. Another frequent mistake is misunderstanding the problem constraints. For instance, if the arrays are sorted, you can leverage this property with a two-pointer technique rather than using nested loops. Additionally, off-by-one errors are a common pitfall when iterating over indices or calculating ranges. Always ensure that you're within valid bounds for both I and j. Don't forget edge cases either. These include empty arrays, arrays with all elements equal, or single-element arrays. Lastly, some solutions might implicitly use extra space, such as recursion stacks or temporary data structures. Be sure to account for this in your space complexity analysis. In an interview setting, there are key strategies that can help you stand out. Recognizing patterns is essential. Many problems involving two arrays can be simplified using techniques like two pointers or binary search, especially when the arrays are sorted. It's also important to focus on finding a correct solution first before worrying about optimization. This demonstrates your understanding of the problem. Once you have a working solution, then shift your attention to improvements. Discussing trade-offs, such as time versus space complexity, shows that you're mindful of constraints and can think critically about your approach. Communication is equally important. Clearly articulate your thought process, especially when addressing edge cases or explaining why a chosen method is valid. For example, if you use two pointers, explain why this guarantees correctness for sorted arrays. This clarity can make a significant difference during interviews. This problem has connections to several related problems, which can help reinforce your understanding of different techniques. For instance, LeetCode 1-2 sum is a classic problem that introduces the idea of using hash maps for efficient lookups. LeetCode 167-2 sum 2 input array is sorted, builds on this by optimizing with a two-pointer approach for sorted arrays. Another example, LeetCode 881, votes to save people, is a problem where sorting and the two-pointer technique are crucial for efficiency. LeetCode 42, trapping rainwater, demonstrates how optimization with two pointers can be applied in a different context, focusing on water trapping instead of arrays. Lastly, LeetCode 34, find first and last position of element in sorted array, showcases the power of binary search in locating specific indices efficiently. Studying these problems can deepen your understanding of when and how to use these techniques effectively. There are several alternative approaches to solving this problem, each with its own trade-offs. The two-pointer technique is highly efficient for sorted arrays, reducing the time complexity to O(n) by iterating through both arrays simultaneously. However, this method is only applicable when the arrays are pre-sorted. Binary search is another powerful approach. By searching for the smallest j for each I that satisfies the condition, you achieve a time complexity of O(n log n). The trade-off here is that binary search implementations can be slightly more complex than using two pointers. Hashing is another option, where hash maps enable faster lookups by storing indices and values. While effective in some scenarios, this approach increases space complexity to O(n). Sliding window techniques are also worth considering, especially if the problem involves subarray sums or ranges. Sliding windows avoid redundant calculations, but they require careful management of bounds to ensure correctness. Each of these methods offers unique advantages depending on the constraints and requirements of the problem. To summarize, we explored the problem maximum distance between a pair of values, discussed various approaches, and analyzed their complexities. Remember to always look for ways to optimize your solution and understand the trade-offs of each approach. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!